Welcome back, everybody.
Welcome back.
We're getting into some powerful stuff today.
Power supplies.
Power supplies. So we're going to talk about
Powerful power supplies.
yeah, we're going to talk about how we supply given voltage and current to the various components within whatever we're working with. So when we're talking about DC, oftentimes we have to come from the wall that's an AC. We have to translate that into a different voltage that is, and then translate that into something that is a current, like a constant voltage to get DC.
Make it usable.
So, in order to change voltage, we use transformers with AC. And we've already talked about, that's one of the things that we need to do here. So we will start by talking about what a transformer is, why we need them, what they do, and how they work. After we get done talking with that, we'll talk about the other parts of a power supply that are only really used for DC, and that's rectifiers and other filters to level out that voltage to be constant. So the first part of this, we're going to be talking about transformers. So let's move on to the next slide. We'll talk about transformers, why we need them.
Well, as we just talked about, we use that to transfer an energy from one circuit to another.
Yeah. So transformer is just allows us to make that transfer from one circuit to another and using electromagnetism, which we've already talked about in another video. And this transfer takes place with a change in voltage, but no change in frequency. And the transformer allows us to send a specific voltage in and get another separate voltage out, which is really cool.
Very efficiently.
And it does that very efficiently with very little loss. So from a power perspective, we can have the same power out as we do coming in, more or less. However, we can have greatly different voltages going in and going out. And this is a huge deal compared to DC circuits, because in DC circuits, well, in order to change the voltage, we need to basically eat up that extra voltage.
Yep.
We consume that and dissipate it as work with a resistor. Here we can do it without loss, so we're not wasting energy.
Yeah, and it's pretty awesome. It's actually pretty incredible how you're able to take something and make more of it with the original source. And you're like, how can you make more voltage, right? Or step it up or step it down, with the same amount. Well, that's where electromagnetism comes in, right?
That is exactly where it comes in. So there's two main types of transformers. And in reality, they're not really even different from one another. It's just how you wire them up. You've got step-down transformer, and a step-down transformer is anytime you're changing the voltage from a higher voltage to a lower voltage.
And then typically what you see at your house.
Yeah.
Right?
And a step-up voltage transformer is stepping up a voltage that's lower to a higher voltage. And the way that it works is just basically how you wire it.
Yeah.
One
more
way
or
or the
less windings.
The number of windings. So we'll get into this when we actually start looking at the actual windings themselves. So let's talk a little bit about the how. Obviously, this sounds too good to be true.
Man, but it is true.
But it is true. It's fairly straightforward, but and it seems like there's a lot of rules, but the rules are kind of all fairly uniform. Like when we compare them to other things in electricity, like these are nice. Yeah. Like these are pretty straightforward. So transformers use electromagnetism to create electromagnetic induction. So it uses those same two principles that we covered in electromagnetism. When we're talking about motors, it still applies here. So let's hit the next slide. So in this case right here, the primary coil generates a magnetic field. Now notice we have AC on this. And what happens is the direction of that flux path the current is flowing in one direction, and then it switches and goes in the other direction. So it's going back and forth, which has the effect of making that magnet, that flux path, move and change directions inside that coil of our secondary coil. So the primary coil generates a magnetic field. We have that hooked up to a voltage of AC. And then the secondary coil is having the magnetic field that was generated by the primary induce a current onto it. So let's look at this. Next slide. The more current, the stronger the field, right? If we double the wires, we double the current. We already kind of talked about this when we were talking about electromagnetism, but think about what that means here. And when we talk about the strong magnetic fields, this should also trigger us back to this wonderful slide that we're going to see next again. We're looping a coil, and we're working up to that slide.
Yeah.
We're working up to this slide where you can loop it around into a coil, and now we're going to get back to our wonderful slide where we've got the cross section of a coil, and this creates those conveyor belt loop items there. And we did a whole dance on this in the electromagnetism video, but this is how a coil works when there's nothing in between. It's because there's only air in there, right?
So you need a medium in there. You need something to
And
transfer that.
you know, we could put an iron rod through there. It would still do the same thing because then we'd have air on the outside. So let's take a look at what we're doing when we're doing the iron core that we do to it, because air is a crappy conductor of magnetism.
Yeah, not good. Molecules is too far apart.
Too far apart. And the one thing that conducts magnetic fields better than anything is iron.
I agree.
So here is our iron core. Now notice the difference here versus the other one. The iron core is such a good conductor so that it takes the magnetic field and concentrates it all the way around in a racetrack loop here. So we've got our magnetic field now going, instead of those two lanes splitting off and going around in two different directions, they're now concentrated and they're going around the racetrack in parallel with one another. And it's because we've given them a racetrack to go on.
If you ever wonder why those things are so heavy,
Because they're iron.
because they're iron, and then you got add the copper windings to that. So
And likewise, when we're talking about motors, you know, we take advantage of the fact that iron is the best magnetic conductor. There's a reason why we have a magnetic field here on Earth. It's because we have an iron core. And
yeah, we've all seen that with like some of those home science kits with the iron shavings in them, right?
Yeah.
So you can visualize the magnetic field around a magnet. You know, if you were a kid and once had one of those kits,
Yeah.
it's pretty cool to see. But iron, again, very good.
yeah, so like if a magnetic field can travel through iron, it will. It's like iron is the copper of magnetism.
That's a good way to put it.
So, yeah, there we go. So this is how we get power from one side of the transformer to the other. So if we look at this, we've got a magnetic field that's going through the other side of it. Now, let's hit the next slide. This is the key here. A magnetic field has to, a moving magnetic field causes electrons to move. A stationary one does not, because it's an attractive repellent force, right, with those
I
electrons.
think there's another dance there.
There's, what is it?
Shimmy?
Is it?
I don't know
I
what
think
it's
this is mashed potato.
Yeah, maybe. I think I might.
I don't know. But you have to have it moving. And so only a changing magnetic field can generate current.
I think as we noted in that other video where you're passing the magnet over the coils that were
Yeah, it needs to be moving.
Needs to be
When it was holding it still, you don't induce current. And so rather than having motion involved in it, if we want to induce a current in a secondary coil, we have to make that
alternate.
magnetic field flip-flop,
Yeah.
right? So if we don't have a sine wave, if we don't have AC, we don't get anything out of our primary, like out of our secondary coil. Like we can magnetize it and metal will stick to it,
Mhm.
but it won't induce current unless it's moving, unless that magnetic field is moving. And so for this, we need a sine wave. If there's no sine wave, there's no dice.
I agree.
So when we have a sine wave, it's constantly changing which direction it's going, forward or backwards. Those little arrows on the blue lines are constantly flipping back and forth from one direction to the other. And as a result of that,
Induces current on those coils.
it induces current on the other coils on the other side. And so we get AC sine wave coming. If we have AC sine wave in, we've got DC or AC sine wave going out. So that covers how a transformer functions.
And that's kind of cool because there's no moving parts there. So
No moving parts, but we've got a moving magnetic
you
field.
have a moving magnetic field, but you don't have anything that's going to wear,
Nothing wears out.
and those things are going to be there for a while.
As long as you don't do anything to put enough current through it
Yeah.
to melt the wires,
True. Yeah.
which I've seen, like then we're okay. Then
Yeah.
you're okay.
And I think that's what we're going to talk about, specifications and,
Yeah,
using the right type of transformer.
Using the right type of transformer through things. So let's look at some of the rules, because we got to have rules. The strength of a magnetic field depends on the number of turns on the primary side. And the induced voltage is dependent on the number of turns on the secondary side. And so it winds up to be a ratio between the two of them, right?
Pretty simple.
Pretty simple. So the number of the turns on the primary versus the number of turns on the secondary is going to tell you how much it steps up or steps down. And if we look at that in terms of numbers, we can see the voltage of the secondary over the voltage of the primary equals the turns of the secondary over the turns of the primary. So if we just keep those straight, keep them on the same side, like it's okay. It works out really well. So if, for instance, we had twice as many, if we have 5 coils on the primary,
10 on the
10
secondary.
on the secondary, we're going to get 2 times the voltage out of it. It's so
This
if
would
we
be a step up.
this would be a step up. So we're going to get, if we put in, let's say 120 volts, we're going to get on the other side 240.
Conversely,
And then conversely, if we swap that around, and notice this is still the same transformer, it's just switching which one is which. But on our primary coil, that's the one you energize. The primary coil has 10 and the secondary coil has 5. Then we get 0.5. So we get half the voltage. So if we put 120 into this primary coil, we're going to get 60.
Mhm.
Now, with current, it's just the primary amps and the number of turns, right? So IP times N, and this makes sense because it's really just kind of substituting in things with Ohm's law. Our current is going to be times the number of the primary, and the current is going to be the turns of the secondary. So essentially it is working like just like with Ohm's law, right? When we talk about like needing more voltage, we're going to use more current. Or I'm sorry, when we're dealing with something that requires more current, we let me start over again. My brain just did a
That's all right.
bloop on me.
Reboot and we're back.
Reboot and we're back. And we're back. So if you've got if you've got a load that is that it requires a certain amount of power, and we hold voltage the same, and it's going to adjust current for that. If we adjust voltage, then the current is going to be less.
Yes.
We saw this with, like, say if you've got a 20-watt light bulb, or I don't want to do math on the fly here, but if you've got a watt light bulb and you hook it up to 1 voltage supply, let's say you hook it up to a 12 voltage supply, and then you hook it up to a 24 volt supply, it's going to require half the number of amps to run that light bulb off of the 24 volt
Than
it would for the 12. So that's just the relationship with Ohm's law. We're all familiar with it. Sometimes my brain reboots, but we got it.
We're not creating any new calculations here. This is all standard stuff you guys have been through.
You've already been through this. So this is just an application of what you've already been through with Ohm's law here, because the power on the one side equals the power on the other side.
As you can see
The
here.
power on the primary equals, and this is where we're applying power law to Ohm's law here. And these are just additional substitutions of these. And you can use these based upon whatever you're trying to figure out through a transformer. But they're all fairly straightforward substitutions.
Really straightforward, easy math, nothing complex.
Like you know P equals I times V. You know that.
And if you don't, revisit your power wheel.
And just keep in mind that on a transformer, P equals P.
Yeah.
And if P equals P on both sides of that, IV on one side equals IV on the other side. So maybe we should have just swapped these 2 slides.
Yeah,
I think
maybe.
my brain wouldn't have like fizzed
Yeah, right.
if we'd kept
Yeah.
these slides in a different order. Okay, next slide. So the application.
You guys see these all the time when you're driving down the road.
What do you think this is? You probably have something like this running, like behind your house. Those are transformers. Those little round things with the spiky antennas coming off of
Look
them.
like square gray bunnies.
Yeah. Those things are transformers.
Yeah.
They're there to translate the power to a lower voltage for what you consume.
Yeah, because you got those high voltage transmission lines that are coming in to parts of your area, and they need to be transformed down to
Yeah.
usable voltage for your home, right?
So why is it so high voltage in the first place?
Well, it needs to be transmitted long distances. So,
Yeah.
in order to do that, that's why you have these big towers that carry these lines. If not, if we were to use DC, and that would require a lot more work, a lot more infrastructure.
Yeah, I mean, like, it comes down to that basic relationship that we were just talking about with current and voltage.
Yeah, that's right.
If we have a wire and we need to send more current through it, we need to make that wire thicker and thicker and thicker.
Because you got a lot more electrons flowing through there.
We can send large amounts of voltage through a wire as long as it's low current. So if we step up the voltage, we reduce the amount of current that is going across the transmission line. And so that's why we do that step up. Our transmission lines are really high voltage, and it's so that we don't have to make these huge wires for them to travel down. If we did, we would probably use up all the copper in the world, and things wouldn't work. Things wouldn't work well. So like the whole argument that Edison and Tesla had was useless, because the moment we went for an economy where we're like producing power at power plants and somehow delivering it over long distances to our homes, we needed transmission lines, and we were going to need to use AC, because I don't think I've ever seen a wire big enough. Like, it would certainly be probably the diameter of this building
Yeah, it'd be way too big.
to transfer what we need on high voltage lines. So it's far easier to just deal with all of these little windings to transfer. We step up the power to go to those transmission lines, and we step it down when we get to your house. And those transformers, they still have rules applied to them, right? We can't draw infinite current on each one of these things, because all of those individual wires on them will melt.
Mhm.
I've seen this happen.
Yeah.
Anybody who's seen something happen like this, like a squirrel will get up there and it'll get in between those two little spiky antennas on top.
Quick arc and everything.
And
goes,
pretty soon that becomes part of the circuit. And yeah, boom goes the transformer because we started drawing infinite current.
Yeah, didn't you have a story about that? That you, you're on
Yeah,
vacation.
I was on vacation. I was on vacation in Panama. It just got done raining. I was on a balcony on the 3rd floor. And I was just watching the clouds from the storm recede. But the power pole was right next to the balcony, like right off to the left of the balcony. And this vulture comes and just kind of soars, and he banks in between the two leads of those that transformer.
Mm-hmm.
And I watched this vulture explode.
Vaporized.
Like it didn't vaporize, but like feathers flew off. Like, and there was an explosion from the transformer itself, and it blew out the transformer, which was unfortunate because it's not like there was a water tower. There were pumps that were pumping the water up to the toilets on the 3rd floor. So our toilet didn't even work when the power went out.
Wow.
But yeah, I watched this, like feathers go flying, like just, it was cartoony almost, like you see like a bird and like it gets shocked and feathers. Yeah, that actually does happen. The feathers fly off. And I watched this thing plummet down to the ground on the street. I was like, wow, I want to see what kind of damage that did to the bird. And so I ran down the stairs, but even by the time I got down to the bottom of the stairs, a street dog grabbed
I
that.
said, hey, somebody's dropping.
Hey, it's a cooked meal. Yeah. And so he took off down the street with that vulture. So yeah, like those things, like on the high voltage side of things, or even on the low voltage side, if you exceed the current that it's rated for, you're going to blow it up, because all those little windings, they're just wires, right? And if they heat up too much, they'll melt. And if they melt too much, they no longer work.
Yeah, and then we're really dependent on these
Oh yeah.
pieces of equipment, right? If these go down, obviously if the transmission lines go down, that's a whole different thing. But an individual transformer can shut down a lot.
Yeah.
And so.
And because induction works in both ways, right? You could get all of these effects that happen and they cause back EMF that can cause additional strain on the structure. And so you can get these cascading power failures like we see happen when a power failure happens. Oftentimes it happens because there's a surge in one area and that surge kind of gets translated. And then when that area gets drawn down, then everybody else is straining to make up for it, and like cascading failure, transformer after transformer getting overloaded, and they all blow up.
I think they call those brownouts. Is that it?
Brownouts is when you got something that actually like causes a dip. And it can be from a transformer failing. Distantly from it. And like brownouts are bad because everything that we rely on relies on a known input of voltage and a known input of frequency. Brownouts, like the frequency can change or the voltage can change. That's what would dim your lights. So if you ever experience dimming of lights, it's probably because somebody else lost power somewhere else and it's trying to make up for it.
Yeah.
So transformers usually have an H and an X size because either side could be the primary or the secondary. It's just which one you hook up the power to, right? So the H side is what is the high voltage side. So that's going to have more windings. And the X side is the low voltage side, and that's going to have the lower number of windings. And so that way, if you wanted to make it a step up, you would hook up your power to the X side, and then you would get a higher voltage out of your H side.
Right, because you have more.
And your H side would then be your secondary. If you wanted to step down, you would hook power up to the H side.
Flip it around.
Flip it around. There you go. So there you go. That's what we've got.
So frequency, we talked about frequency
Yeah.
in a previous lecture. Something that we can actually listen to when we're standing next to a transformer.
Oh yeah.
You know,
You can hear the hum.
they're singing their own song.
They sing a song and it's really grating and annoying. You can also hear the frequency that's happening, when you weld something. Anytime you're hearing an electrical arc, it's that buzzing noise that is like frequencies are audible.
Yep.
Hertz is how we measure sound as well. So that's 60 hertz. It's just one note.
Yep.
Like it is a one note orchestra. It's the lamest symphony you'll ever hear. And it's really grating and annoying.
Yeah. That's why it's important to make sure that these transformers that you're going to use in any application are the correct ones. And you're making sure you're abiding by the specifications of these transformers.
Because there's and this sort of thing here will make a little bit more sense a little later on when you get to a video about reactance. But essentially there's something called reactance, which is like resistance in AC. And if we use a lower frequency, the reactance will decrease and we'll get a much larger current out of it. This causes, because that's essentially the effect of dropping resistance. If resistance goes down, current goes up. And so that's going to cause the flux density of the core to increase and the saturation will be larger than design. And it could induce a higher current than what the wires are capable of handling.
And it'll melt.
And it'll melt. If a higher frequency is used, the reactance will increase, which means we kind of get a negative resistance associated with that. And so current will decrease, and so we won't get the same efficiency out of it.
Won't be as efficient for sure.
So that's something to keep in mind. And the same will happen if you go above the listed voltage. You do get plus or minus 5% around these things, so don't worry about it if it's not exact. But you've got a little bit of
buffer to play with.
Little bit of buffer to play with before you start frying things, but it doesn't, like, usually the things that set these things off to explode.
Yeah. Don't live on the edge of that.
Don't live on the edge.
Yeah.
Don't live on the edge. Yeah. And then likewise, this slide will make sense, but it has the same sort of relationships as everything else. We haven't talked about impedance yet in AC, and we'll talk about that in a later video. You'll come back and you'll be able to review this slide and really see. The thing that I want to point out here with impedance is that you've got the same relationship where the voltage equals the voltage equals whatever we're looking at here. Voltage equals the impedance where we've got the primary over the secondary windings. It's all just about that. Like everything about transformers boils down to that ratio and the windings of the coils.
As simple as it is, that's what it really comes down to.
Yeah, and so you'll understand that after we get through the impedance one. I don't want to like bog everything down,
Right.
But like this is a chicken and egg scenario.
We'll get there.
We'll get there. After we get there, you can come back to this and this will make sense. If a step-up transformer has a ratio of 3:1, our voltage ratio
1-3.
is going to be 1:3. Our current ratio
3-1.
is going to be 3:1. And then later on, you'll be able to know that your load impedance ratio is going to be a multiplication of those. And if we click on the next slide, here are the answers. 3:1, 1-3, 9-1.
Yep.
All right. I feel like we should take a breath.
Yeah, right. To All right.
Yeah. Okay. So That's transformers.
Mhm.
And transformers do a great job of changing without loss one voltage to another voltage. And when we make that change from one voltage to another voltage, we do change current in the opposite way.
Correct.
When we are trying, so that allows us to do anything that we need to do with AC. For instance, in a lot of older homes, you'll see transformers that are used as a just an AC power supply for your doorbell.
Yeah.
Because your doorbells are like 24 volt AC, whereas everything else in the house is 120 volt
You wouldn't
AC.
want to be running 120 volts through your doorbell, right?
Not through what I push on my finger, right? So yeah, that's an example of a power supply that's just AC to AC is only a transformer. But when we need to go to DC, our power supply needs to become more complex. So we first need to get whatever voltage we want to use out of DC. So we'll go through a transformer. So that transformer will step it down to, in the case of our electrical panels here in class, 24 volts. And then we go through a process called rectification, and that means it straightens the direction of the current. And rectifiers have many uses, but like taking DC power supplies is one of the most common usages. Rectifiers are often used along with an electronic filter, which could be a capacitor, a choke, a set of capacitors, chokes, resistors, following the voltage regulator to produce a steady current. So let's take a look at what this looks like in a circuit diagram. So
if we look here, we can see a standard AC sine wave.
So we would have our transformer hooked up to this. So if we wanted 24 volts DC, we would have hooked up a transformer, and then that would be the supply off of the secondary windings of that transformer. And so that would be 24 volts going in there. And then we've got what's called a bridge rectifier. That's the D1 on there. And that's just a series of diodes. And diodes are one-way valves, right? You know that.
They're the electrical check valves of the world.
And what they do is they basically direct traffic here so that instead of going below zero,
Those are basically
everything,
flipped on
they basically flip on end, and they become just mountains, right? Like all going up. And that's what we see on the right-hand side of the bottom drawing there.
So that's at a really high resolution there.
Yeah.
Typically you wouldn't see that, visible.
Because it's doing that 60 times a second.
Exactly. It's going so fast you're not seeing it.
It's doing, and actually those two humps, it's actually doing, so when you look at that, like each hump there is actually 120th of a second, because it's flipping the negative one up positive. And so there's two humps for every cycle of AC. And then we have what's called the RC shunt filter on this one, and it's a capacitor and a resistor. And what the capacitor and the resistor are doing is they're leveling it out, because the capacitor can charge and discharge. And so the charging and discharging cycle of that capacitor is causing the red line that we see there. The red line that, like, the voltage only dips a little bit
Slightly
in between the humps there, so it's smoothing it out. And if we look at the part up on the upper right hand side here, you're going to see this is what the AC looks like coming in, and you'll see the tiniest little humps there that are happening around the charging and discharging of the capacitor on the RC shunt filter. This is what that output of that power supply is. The yellow is the input, the green is your output. So that's a power supply. So power supply for DC, we could have a power supply that's taking in a voltage. We could have multiple transformers that are transforming multiple voltages, and then we would rectify and filter each one of those to get different voltages of DC coming out of them. And so power supplies are big. We need different voltages. We need different current on different components. And so,
Yeah, it's a lot of times we don't think about all the uses we have for them.
yeah, but like this is what's happening on that little wall wart that you plug in to charge your phone.
Cell phone, yeah.
Like every single one of those has this in it. It has a transformer, it has a rectifier, and it has a filter.
And now you know.
And now you know.
All right.
This is what they kind of look like. In the
Individual
bottom,
component.
yeah, in the bottom left over there, on the bottom left, we've got, and I'm invading your picture frame here. On the bottom left, we have that is just a straight up diode in and of itself.
One-way diode.
And so we would need 4 of those to create a bridge rectifier. And then above that, you'll see that's a more high-powered bridge rectifier with 4 leads on it. And so 2 would be hooked up to AC. And then there's a smaller bridge rectifier next to it. Like these aren't to scale.
No. These are...
But you can see the little squiggles on it. So that means you hook up AC to one side and then you get plus minus coming out the other side. And that's just what it's doing. So you'll see rectifiers of various different kinds. But they're everywhere. They're everywhere. So that's all we've got on that subject. Transformers, more than
Everybody
meet
made
the
it
eye.
through that all right. I think we're at a little bit of a brain fart here and there. But
Yeah, no, my brain, successfully recovered from a massive error. But here we are.
Well, we're human,
We're
so,
done.
All right. Well, hey, thanks for joining, guys.
Thanks for joining.
We'll see you on the next one.
See you on the next one.